So here is a graph of our actual values and predicted values of our model. In this scenario, there are only two possibilities. Number one, first, if the predicted value and actual value are the same, then we are good. No need to worry. Number two, second, if the predicted value is different from the actual value, then we need to find the difference between the values. This difference is called the error or cost function. In order for our model to work accurately, we need to reduce this error. In this case, we get help from the back propagation approach to update weights in our network and reduce this error. So, to sum up, let's keep in mind that backpropagation is an algorithm used to fine-tune mathematical weight functions and increase the accuracy of an artificial neural network's outputs. It is one of the most widely used algorithms in artificial intelligence. Alright, so that was it for the propagation of information in artificial neural networks. And now on to the next lecture. Why is deep learning important? We saw in the previous lecture how deep learning is a subfield of machine learning, which is itself a subfield of artificial intelligence. Now let's see why deep learning is so important in machine learning. Deep learning is very important because it can deal with complexity whereas typical machine learning algorithms cannot. For decades, machine learning has been used for classifying images and text, but there is a threshold point in its performance, and beyond that threshold, it cannot perform well. We do not always deal with a small amount of data. In fact, most of the time the data we have is enormous, and relationships among the data is very complex. In this situation, only deep learning enables us to deal with such data efficiently, as shown in the graph. So, to sum up, many complicated issues may be solved with the help of deep learning, which focuses on analyzing huge sets of interdependent variables to uncover hidden patterns in the data or uncovering complex connections between them. Deep learning algorithms can discover hidden patterns from the data, integrate them, and develop more efficient decision rules. Deep learning excels when it comes to complicated tasks such as picture classification, natural language processing, or voice recognition. Alright, and now on to the next lecture. Talking about the popularity of deep learning, most of the advances in practical application of deep learning have been driven by the availability of widespread, robust, open source software packages. With such rich sources already available, developers prefer to use them and contribute more to them. Lately, data science is moving towards Python, so most of these packages are developed mainly for the Python language. Some of the packages are TensorFlow, Caffe, Torch, Theno, and ConvNets.js. Alright, and now on to the next lecture. Once you are introduced to deep learning, it is time to dig into the complexity of our topic. As stated earlier, deep learning uses a neural network in its execution. So we are going to examine neural networks. Keep in mind that the neural networks is also called artificial neural network. So basically, brain-inspired neural networks are simplified representations of the biological nervous system, consisting of a densely linked network comprising a large number of processing components known as neurons, with an architecture inspired by the human brain. An artificial neural network is a computational model that mimics the way nervous cells work in the human brain. Artificial neural networks are a vital element in all the models in deep learning. They are the fundamental algorithms as well as the simple approaches that are utilized in the deep learning DL approach. Alright, and now on to the next lecture. I assume most of you are familiar with the diagram of a neuron from your school time. Basically, a neuron receives or transmits impulses or information in various parts of our body. Billions of these neurons work collectively to build our nervous system. For example, if your finger is burning on a candle flame, neurons on that finger receives this information, and the information is transported by the ascending neurons to the central nervous system. The central nervous system realizes that something is wrong, so it sends the message back to the arm with the help of descending neurons to stimulate the arm in order to remove the finger from the candle. So to sum up, nerve impulses travel throughout your body thanks to specialized cells called neurons in your nervous system. Your brain, skin, organs, glands, and muscles all communicate with each other through electrical impulses. Movement and feeling, like pain, are made possible by the signals. Hope this gives you a proper sense of how the nervous system works. A neuron in artificial neural network can be considered as a numerical representation of the biological neuron. Both the biological neuron and the artificial neuron can get information inputs and transfer it to the next neuron it is connected to. A simple neuron network is graphically represented on the slide. It consists of some input neurons x1, x2, x3, xn, and one output neuron, y. A neuron is also known as a node. The rest of the elements are collectively called synapses. The synapse is responsible for the connection between input and output nodes. This connection between neurons consists of weights, a transfer function, and an activation function. So this communication consists of W1, W2, Wn, which are weights associated to each input, as well as a transfer and activation functions, which are vital for tuning the data and transporting data between nodes. Weights can be assumed as importance of an input to a node. How important one input is to a neuron is actually defined by the value of the weight. If the weight is 0 for an input, then it means that the input contributes nothing to the value of the node. But if the value of the weight is high for an input, then it contributes a lot to the value of the node. Now, onto the functions. So, functions in the synapse are some mathematical functions. Transfer function is the sum of all the products of each input by its weight. And activation function is a function that takes input from the transfer function and applies a function to the value in order to get another value and send it to the successive node. Weights are very crucial in neural networks because neural networks learn by modifying the values of their weights. And the neural network will then decide to how much a signal is significant in each case. It is possible that all signals are passed, no signal is passed, a low amount of a signal is passed, a high amount of the signal is passed. This is all done by changing weights while algorithms learn. We are able to do so by using gradient descent, GD, and back propagation, BP. In the upcoming lectures, we will learn about the meaning of gradient descent, GD, and backpropagation, PB, in detail. Alright, now on to the next lecture. The architecture of a complete neural network is shown in this figure. It has an input layer which consists of all the input nodes. Next, it has a hidden layer which consists of all the nodes in between input and output layers. And lastly, it has an output layer which consists of output nodes. In this figure, it has only one output node. To briefly summarize how a neural network works, first, signals from multiple neurons such as x1, x2, x3, xn, along with their associated weights w1, w2, w3, wn, transmitted to the successive neurons. Second, once a successive neuron receives those inputs, it sums up all the products of signals and their associated weights. Third, once the sum is calculated, an activation function is applied to the sum and we get a value for this successive neuron. And fourth, the above process keeps on repeating until the last neuron gets a value. I hope that the architecture of the neural network is clear for you now. So we're now familiar with the structure of an artificial neural network. In the upcoming lectures, we are going to see in detail how information propagates in an artificial neural network and how our model learns by itself. There are two important approaches to how a neural network propagates the signal of the input data. One is feed-forward and the other is backpropagation. Number one, the feed-forward network, or FFN, is a network approach where the information moves in only one direction. It moves from input nodes through the hidden nodes, if present, and then to the output nodes. So, there is no other connection that moves the information in the opposite direction and forms cycles or loops in the network. Number two, whereas the backpropagation network, or BPN, is opposite to the feed-forward network. If we do not get the desired result as expected from the feed-forward network, we move backward in the network to fine-tune weights so that we can get closer to the desired output for the same inputs. By doing so, our network learns and adjusts the value of the weights accordingly. In the backpropagation network, the error is computed in the output layer by comparing the predicted values to the actual values. Our objective is to decrease this error as much as we can. So, we backpropagate, then do some adjustments with weights. Then, again, we proceed until we get the minimum error. The backpropagation network is an advanced algorithm which has more complex mathematics for adjusting weights, and one of the main advantages of the backpropagation network is that our network knows which weights contribute to the error. So here is a graph of the actual values and predicted values of our model. In this scenario, there are only two possibilities. Number one, first, if the predicted value and actual value are the same, then we are good. No need to worry. Number two, second, if the predicted value is different from the actual value, then we need to find the difference between the values. This difference is called the error or cost function. In order for our model to work accurately, we need to reduce this error. In this case, we get help from the backpropagation approach to update weights in our network and reduce this error. So, to sum up, let's keep in mind that backpropagation is an algorithm used to fine-tune mathematical weight functions and increase the accuracy of an artificial neural network's outputs. It is one of the most widely used algorithms in artificial intelligence. Alright, so that was it for the propagation of information in artificial neural networks. And now on to the next lecture. There are various architectures of neural networks, so let's go over the different types of neural network architectures to get an idea of what they really are. The simplest type is the single-layer perceptron model. In order to get from the single-layer neural network to the multi-layer neural network, we will first analyze the single-layer neural network. This is also referred to as a perceptron. When it comes to artificial neural networks, the perceptron is the most fundamental one. In a single-layer neural network, or perceptron, the neural network has only input and output layers without any hidden layers. Alright, that was it for the single-layer perceptron model. Next is the radial basis network model. Alright, so what is the radial basis network? These networks are composed of input, single hidden, and output layers. They are a feed-forward neural network which only uses the radial basis function as an activation function. What is an activation function? An activation function decides whether a neuron should be activated or not. And in the case of the radial basis network, a radial basis function, or RBF, is the activation function used. It assigns a real value to each input, and also the value produced by the radial basis function is always an absolute value. Next is multi-layer perceptron neural network. These networks consist of more than one hidden layer of neurons. They are also known as deep feed-forward neural networks. So, to sum up, multi-layer perceptron neural networks are made of an input layer and output layer, and a number of hidden layers in between the two. Hidden layers are the real computational engine of multi-layer perceptron neural networks. Alright, so that was for the MLP, and now on to the recurrent neural network. Recurrent neural networks process memory. The value of a hidden layer neuron is a combination of data it receives from the lower layer and its previous value. Previous value contributes to the current value, and it's exactly this feature that enables the neural network to process memory. So, to sum up, RNNs are a type of artificial neural networks that may be used to analyze time series data or data that involves sequences. When you use an ordinary feed-forward neural network, you need to have a large number of independent data points. However, if the data is arranged in a way that each data point is dependent on the one before it, we will have to make changes to the neural network to account for these interdependencies. This memory lets RNNs keep the track of prior inputs so that they may create next a new output in the sequence. Next is long short-term memory neural network, LSTM. The type of neural networks in which the memory cell is incorporated into hidden layer neurons is called LSTM network. Keep in mind that LSTM is a particular type of the recurrent neural network, or RNN, that we saw in the previous lecture. This particular type of RNN, known as LSTM, is able to learn long-term dependencies via the use of the short-term memory networks. Hochreiter and Schmid-Huber 1997 were the first to present it, and many others have since improved and popularized it. Long short-term memory networks are now frequently employed because they work so effectively on so many different types of issues. By design, LSTMs do not suffer from the long-term dependency issue. It is not like they have to work hard to learn how to retain knowledge for lengthy periods of time. Alright, so that was it for the long short-term memory networks, and now on to the next lecture. Okay, so next is the Hopfield Network. Keep in mind, the Hopfield neural network is a special type of the recurrent neural network, or RNN, that we saw in the previous lectures. The Hopfield neural network is different from other neural networks. The number of neurons is the same as the number of inputs and outputs. That said, we then have the same number of inputs and outputs. So the Hopfield neural network is a fully interconnected network of neurons in which each neuron is connected to every other neuron. The network is trained with input patterns by setting a value of neurons equal to the value of the desired pattern. Then the weights are computed through deep learning algorithms. Alright, so that was it for the Hopfield network, and now on to the next lecture. The last one is the Boltzmann Machine neural network. These networks are similar to the Hopfield network, except that some neurons are directly connected to inputs, while others are not associated to inputs directly. The weights are initialized randomly and learned through the backpropagation algorithm. Alright, so to sum up, Boltzmann Machine neural network is also a type of recurrent neural networks. It is composed of nodes that make binary judgments and are predisposed to particular biases. Alright, so that was it for the Boltzmann's machine, and now on to the next lecture. Our next topic is one of the crucial components of machine learning and deep learning. It will be about activation functions. So what does an activation function do? It helps a neural network to learn complex patterns in the data. The activation function takes inputs from the output signal of previous neurons and converts them into some form that can be taken as input to the next neuron. So, it takes some input and applies some function on that input to get a result, and this result is transferred to the next neuron. The activation function is also known as a transfer function. Well, activation functions can be classified into linear activation functions and non-linear activation functions. A neural network with no activation function is linear in nature, like polynomial of 1 degree, or as a linear regression model. But keep in mind that linear functions have less power to learn complex functional mapping from data. One of the main purposes of activation functions is to introduce non-linearity to the output of a neuron because real-world problems are non-linear, high-dimensional, and complicated. So, by using non-linear activation functions, the neural network will be better equipped to mimic the real world accurately. To understand the non-linear activation function, we need to know the following terminologies. Number 1, differential function. It represents the change in the y-axis with regard to the change in the x-axis, so it's basically the slope. Number 2, monotonic function. When a function is increasing on its entire domain or decreasing on its entire domain, we say that the function is strictly monotonic, and we call it monotonic function. Now, let's explore the activation function one by one. The first is the sigmoid function. There are some important characteristics of this function that we need to keep in mind. First, the range of this function is limited to greater than 0 and less than 1. Second, the range is 0 to 1, so it is especially used for models where we have to predict the probability as an output. Third, it's a differentiable, which means we can find the slope at any 2 points. Fourth, it is a monotonic function. Fifth, it is not very useful in the real-world examples because of the following 3 reasons. It's computational inexpensive. It is not zero-centered, which means the range only consists of either positive or negative values. It causes vanishing gradient problems. The vanishing gradient problem is encountered when an artificial neural network is trained with gradient-based learning methods and backpropagation. In such methods, each of the neural network's weights receive an update proportional to the partial derivative of the error function with respect to the current weight in each iteration of training. In the worst case, the gradient value will be so small that it might not be able to change any weight. So, to sum up, the sigmoid function will always output a value between 0 and 1, regardless of any real number input. Basically, any real number will be converted to a number between 0 and 1. Hence, the sigmoid function is said to squeeze values. Alright, that was it for the sigmoid function. Now on to the next lecture. Next is the hyperbolic tangent function. It is considered to be a better version of the sigmoid function because it ranges from -1 to 1, whereas the sigmoid has a range from 0 to 1. Similarly to the sigmoid function, the hyperbolic tangent function is also a differentiable function and is also a monotonic function. Additionally, note that there are applications where the hyperbolic tangent function is advantageous since it falls below 0. For example, negative inputs are mapped strongly negative, and 0 inputs are mapped near 0 in the hyperbolic tangent graph. This is definitely an advantage since it maps the negative inputs extremely negative. That being said, the hyperbolic tangent function is mainly used for classification between 2 classes. The hyperbolic tangent function is used in feed-forward propagation in order to increase the difference between outputs. Next comes the softmax function. First, this particular activation function works in the output layer. Second, it applies a standard exponential function to all the values in the output layer. Then it does the normalization by dividing each value by the sum of all exponentials. So, this way, all values sum up to 1. Third, it computes the probability or confidence score for each attribute, so it is used in multi-class classification problems. Fourth, it is also a differentiable function. Alright, so that's it for the softmax function. Now on to the next lecture. The next one is the rectified linear unit, or RELU function. Number 1, if the value is less than 0, then the function becomes 0. If the value is equal to 0 or greater than 0, the function becomes the number. Number 2, it is commonly used in convolutional neural networks, which we'll explore later in this course, as well as in deep learning approaches because it does not cause vanishing gradient problems. Number 3, it is also a differentiable function. Number 4, but it is not a monotonic function. Number 5, the range of this activation function is from 0 to infinity. Number 6, one problem with this function is that we lose data that is less than 0 and our neural network learns nothing from those neurons. Moreover, it maps all the values lesser than 0 to 0. This approach is not proper because it makes our neural network unstable. Alright, so that was it for the rectified linear unit, RELU function, and now on to the next lecture. The next activation function we are going to explore is the Leaky version of a rectified linear unit function. Number 1, this is a modification of the RELU function. It solves the negative impact of the rectified linear unit function. Number 2, usually the value for A in the diagram is around 0.01. Number 3, range of Leaky RELU is from negative infinity to positive infinity. Number 4, it is also a differentiable function. Number 5, and it is a monotonic function as well. Alright, now on to the next lecture. The most amazing characteristics of machine learning is that it can learn by itself. In the upcoming lectures, we are going to understand how a network adjusts its weights and learn by itself. Gradient descent is one of the most popular optimization algorithms in machine learning and deep learning. In other words, it finds the values of a function's parameters, coefficients, that minimize a cost function as far as possible. You start by defining the initial parameters values, and from there, gradient descent uses calculus to iteratively adjust the values so that they minimize the given cost function. To see how gradient descent works, assume the graph is a cost function of our model. Blue dots imply different iterations, where different weights are adjusted on each iteration. We will get a different cost function on each point because it is changing weights after each iteration. It takes an initial value of the function and applies the formula shown on screen. B equals A minus gamma Laplace operator function over A. From the current position, we either move forward or backward, and the size of our step is instructed by the gamma Laplace of the function of A. We can also assume that the size of the step is defined by the value of the gradient, or slope. If the gradient is high, our step size is also large, and vice versa. After some steps, we'll be able to reach the minimum value. The main drawback of gradient descent is that it is limited to a convex function in terms of the shape of the function. For a non-convex shape, as shown on screen, gradient descent is not going to produce the desired result. Because we have multiple minimal values, local minimal values, and in this case, gradient descent might not find the optimal minima, global minimum, from the shape. For this kind of situation, we mostly opt for the Stochastic Gradient Descent Optimization Technique, SGD. As the name stochastic expresses, this technique has some randomness. In the stochastic gradient descent technique, we find out the gradient of the cost function of a single input at each iteration instead of the sum of the gradient of the cost function of all inputs. With the stochastic gradient descent, since only one sample from the data set is chosen at random for each iteration, the path taken by the algorithm to reach the minima is usually noisier than your typical gradient descent algorithm. But that doesn't really matter because the path taken by the algorithm does not matter, as long as we reach the minima and with a significantly shorter training time. Typically, stochastic gradient descent takes a random single value at a time. If the algorithm takes a subset of values rather than a single value, in this case, it is known as mini-batch gradient descent. One important difference between gradient descent and stochastic gradient descent is that in gradient descent, for every iteration, we take the whole data set to measure gradient and update parameters of the cost function. While in stochastic gradient descent, unlike in gradient descent, we take a single value or a subset of values in an iteration to measure gradient and then to update the parameters of the cost function. So, if the data is very large, gradient descent may take too long. In this case, stochastic gradient descent would be the faster. We have completed the theoretical part of deep learning. Now, before going to the implementation, let's review what we have learned so far. So let's do it. First and foremost, let's review how neural networks work. It consists of a number of simple but highly interconnected elements or nodes called neurons. Those neurons are organized in layers which process information using dynamic state responses to external inputs. The first layer is the input layer. The last layer is the output layer by default. Assume that we need to calculate the price of the house and we don't have a hidden layer. Let's say inputs are 1. The area, 2. The number of bedrooms, 3. The distance from the city, 4. The amenities available, 5. The age of the property, 6. Hospitals for kids, and 7. Schools for the kids. So the price will simply be the summation of the product of inputs and their weights respectively. This is an approach that is used in machine learning models. Now, what makes the deep learning approach better than the machine learning model is the addition of a hidden layer. It gives some flexibility and power to increase accuracy. Let's consider estimating the cost of the house for the same example with an artificial neural network. All input neurons are connected to all the neurons in the hidden layer. The neurons in the hidden layer won't have the same values as the ones in the input layer. because depending on the importance of the inputs, we will have different weights. So, depending on priorities of inputs, the weighting values change, and then the hidden layer changes accordingly. Now, each neuron in the hidden layer also has some priorities and weighting. Now, in order to improve the accuracy, it is necessary to increase the number of hidden layers for some significance or weighting, or for doing difficult calculations. It is similar to fine-tuning the network in order to get the best possible output. On your screen, you can see the detailed workflow of an artificial neural network. In step 1, each neuron in the input layer holds the value of each attribute from the data. In step 2, summation of the products of each of those values along with their respective weight is calculated. Then, this summation value is put to an activation function to map it to another value. In this example, the activation function is sigmoid. In step 4, output of the activation function is forwarded to the next neuron. And all of these 4 steps repeat until it reaches the output layer neurons. So, during our previous lectures, we explored in detail artificial neural networks. What are the advantages of artificial neural networks? They have the ability to work with incomplete knowledge. After the artificial neural network is trained, the data may produce output even with incomplete information. The loss of performance here depends on the importance of the missing information. Next is fault tolerance. Fault tolerance means the corruption of one or more cells of the artificial neural network will not stop the generation of the output. Then we have parallel processing capability. An artificial neural network can perform more than one job at a time. Alright, so that was it for the advantages of artificial neural networks. Now on to the disadvantages. So, regarding the disadvantages of artificial neural networks, first is the hardware dependency. Artificial neural networks require processors with parallel processing power, in accordance with their structure. For this reason, the realization of the equipment is dependent. Next is the determination of proper network structure. There is no specific rule for determining the structure of artificial neural networks. Appropriate network structure is achieved through experience as well as through trial and error. Now, regarding the applications of artificial neural networks have so many applications in the real world. Some of the important ones are: number 1, handwritten recognition. Number 2, image compression. Number 3, stock exchange prediction. The idea of handwriting recognition has become very important. This is because handheld devices like pads, notebooks, tablets are becoming very popular. Hence, we can use neural networks to recognize handwritten characters. Now, regarding image compression. These days, vast amounts of information are received and processed at once by neural networks. This makes them useful in image compression. With the internet explosion and more sites using more image on their sites, using neural networks for image compression is worth a look. Another important application is the stock market. The day-to-day business of the stock market is very complicated. Many factors weigh in whether a given stock will go up or down on any given day. Thus, neural networks can examine a lot of information in a fast manner and sort it all out, so we can use them to predict stock prices. Alright everybody, quiz time. What do you think is the most appropriate definition of a back propagation amongst the options given in the slide? Ready with your answer. The answer is C, as we have learned in this course. I hope that by now you have developed a strong understanding of how ANN works. Assuming so, let's learn the implementation of ANN through Python coding. Slide 46. For the implementation in Python, I'm going to use the churn modeling dataset. You can download the dataset from Kaggle. Artificial neural networks can be used for both classification and regression. And here we are going to use ANN for classification. Alright, so now that you download the dataset, you can double click on it, open it and see what's inside. We can clearly see that this dataset has the following attributes. 1. Customer ID. 2. Surname. 3. Credit score. 4. Geography. 5. Gender. 6. Age. 7. Tenure. 8. Balance. 9. Number of products they used from the bank, such as credit card or loan, etc. 10. Has credit card or not? 1 means yes, 0 means no. 11 is active member. That means the customer is using the bank or not. And 12, estimated salary. So these are all the independent variables of the churn modeling dataset. The last feature is the dependent variable, and that is customer exited or not from the bank. 1 means the customer has exited the bank and 0 means the customer stays in the bank. The bank uses these independent variables and analyzes the behavior of customers to see whether they leave the bank or stay. Now the bank has to create a predictive model based on this data set in order to predict the behavior of new customers. This predictive model has to predict for any new customer whether he or she will stay in the bank or leave the bank, so that the bank can offer something special for the customer whom the predictive model predicts that they will leave the bank. I hope now you understood the problem statement. So, the first step in the implementation of an artificial neural network in Python is data pre-processing. Data pre-processing involves transforming raw data to well-formed data sets so that the machine learning and deep learning algorithms can be applied. There are some important libraries in Python which are used to play with data. 3 of such libraries are displayed on the screen. First is NumPy, which stands for Numerical Python. It is used to perform various mathematical and scientific tasks. NumPy is used for working with multi-dimensional arrays. It also has functions for working in the domain of linear algebra and matrices. Matplotlib is second. It is a plotting library that is used for creating a figure, plotting area in a figure, plot some lines in an area, decorates the plot with labels, and much more. Third is Pandas. It is a library that offers us tools used for data manipulation and analysis. If you don't have Python already installed on your device, you can visit www.anaconda.com to download the world's most popular data science platform, Anaconda. Anaconda is a bundle that contains Python implementation as well as the popular tools and libraries used in data science, such as Jupyter Notebook. It is like an all-in-one package. Installing Anaconda will install Jupyter Notebook, Python, and the popular data science libraries like Panda, NumPy, and Matplotlib, etc. on your machine. In this course, we will be working in Jupyter Notebook. Jupyter Notebook is a web-based application. Its cell-based structure allows you to write and run code, create visualizations, and have narrative text all at one place. We will be using Anaconda distribution to set up Jupyter Notebook on our machines. So, after you install Anaconda onto your computer, search for Anaconda Navigator in your search bar and open it. Inside the Anaconda program, or Anaconda Navigator, you will see a tab called Jupyter. Launch your Jupyter Notebook by clicking on Launch. It will launch Jupyter Notebook in your default web browser. Click New, and then Python 3 to create a new notebook. Alright, so we're now set up. Let's import the essential libraries that we'll need for this project. Import NumPy as NP. Import matplotlib.pyplot as PLT. Import pandas as PD. Click Run. And here you go. We can now use the library's features in our notebook. So that was our first step. We imported all the required libraries. Now in the next step, we'll need to import our data to Python. We import the dataset using a function called read_CSV from the pandas library. Dataset equals pd.read_CSV brackets churn_modeling.csv close brackets. We just create a variable called dataset, in which we store the whole dataset CHRUN_modeling.csv You can see that in our dataset there are 13 independent variables and one dependent variable. But the first three independent variables, row number, customer ID, and surname, are useless for our prediction because they do not contribute for a user to stay or leave the bank. Row number, customer ID, and surname do not help in predicting the behavior of a customer, so we will eliminate these three independent variables in the next step. And we will also split the independent variables in X and the dependent variable in Y. So, to split the dataset into independent and dependent variables, we need to write the following. X equals dataset.iloc square brackets open colon comma 3:13 close square brackets dot values. Y equals dataset.iloc open square brackets colon comma 13 close square brackets dot values. The dataframe.iloc method is used when the index label of a data frame is something other than the numeric series of 0, 1, 2, 3, n, or in case the user doesn't know the index label. Why do we have dataset.iloc open square brackets colon comma 3:13 close square brackets dot values for the variable of X? Because attribute credit score has an index value of 3, and we want the features from credit_score to estimated underscore salary. So this first line of code takes all the data from the column 3 till 13, not including 13, and store it in the variable x. In the second line, it is similar to the first line. Here, it puts all values of the column number 13 to a variable called y. To better understand what's inside the variable x, let's print x on the screen. So we write print brackets x. And here you go. As expected, we have all the information from the credit score, column till the estimated salary column. Now, to better understand what's inside the variable of y, let's print y on the screen. So we write print brackets y. And here you go. As expected, we have all the data from the exited column of our dataset. As said previously, y represents the dependent variable. In this image, we have the data inside the variable x. You can see this data set starts from credit score and ends with the estimated salary. It's exactly what we just saw in Jupyter Notebook. And this is how variable y will be holding values. Also, it's exactly what we just saw in Jupyter Notebook. Alright, so now we have successfully divided our dataset into x and y. Let's move on. All of our input attributes are numerical values except geography and gender. So we need to somehow transform these values to numeric as well, in order for our algorithms to work properly. This process is called encoding. For instance, in case of gender, we can assign the label 0 to female and 1 to male. Such encoding is called label encoding. And in case of geography, we will be doing hot encoding, which is a bit different than label encoding because in this encoding, each label is represented by an array of integers rather than a single integer, as in a label encoding. Thanks to the sklearn library, we can encode values by ourselves. sklearn is the most robust library for machine learning in Python. It provides effective tools for machine learning and statistical modeling, including classification, regression, clustering, and more. On the slide, you can see that we're importing the label encoder and one hot encoder classes from the sklearn.preprocessing library. Here our objectives is to transform the string's values of attribute gender to numerical form using the label encoding method. In the second line, we have created an object, label encoder underscore x underscore 2 of the class label encoder. In the last line on the left hand side of the equation, we are assigning values to the third column of the variable x. On the right hand side of the equation, we are using the fit underscore transform function of the class label encoder. This function returns values after mapping them. In other words, it maps string values to numerical values. In our case, we are replacing string values of attribute gender, which are female and male, to numerical values of 0 and 1. So after performing label encoding on the gender variable, the male and female are converted into 0 and 1. Let's go to Jupyter Notebook and see how this works. From sklearn.preprocessing, import label encoder, comma, one hot encoder, label encoder underscore x underscore 2 equals label encoder. x open square brackets colon comma 2 close square brackets equals label encoder underscore x underscore 2 dot fit underscore transform brackets x open square brackets colon comma 2 close square brackets close all brackets. Let's print the variable of x, which presents the independent variables in our model. So we write print brackets x. We run this cell, and here you go. We now have the same data set as previously, with only one difference. The male and female that you see up here have now been converted to 0 and 1. You can see it down there. 0 represents female and 1 represents male. Now we have one more categorical variable, and that is geography. So, to resolve this issue and get only numerical values, we will need to perform one-hot encoding to convert France, Spain, and Germany into the 0 and 1 form. Let's see how we can do that. Alright, so now to implement one-hot encoding, we'll need the help of the column transformer and one-hot encoder libraries from sklearn. Let's move on to Jupyter Notebook to see how this works. First, let's import column transformer. We write from sklearn.compose import column transformer. Then we write ct equals column transformer open brackets open square brackets OHE comma one hot encoder close brackets square brackets 1 close square brackets close brackets close all square brackets. Remainder equals pass through close all brackets again. Here we are creating an object of the column transformer class. But before we can do that, we need to understand the column transformer constructor takes quite a few arguments, but we're only interested in 2. The first argument is an array called transformers, which is a list of tuples. The array has the following elements in the same order. Name, a name for the column transformer, which will make setting of our parameters and searching of the transformers easy. Transformer. Here we're supposed to provide an estimator. We can also just pass through or drop if we want, but since we're encoding the data in this example, we'll use the one-hot encoder here. Remember that the estimator you use here needs to support fit and transform. Columns. The list of columns that you want to be transformed. In this case, we'll only transform the first column. The second parameter we're interested in is the remainder. This will tell the transformer what to do with the other columns in the dataset. By default, only the columns which are transformed will be returned by the transformer. All other columns will be dropped, but we'll have the option to tell the transformer what to do with the other columns. We can either drop them, pass them through unchanged, or specify another estimator if we want to do some more processing. As you can see from the snippet above, we named the transformer simply OHE. We're using the one-hot encoder constructor to provide a new instance as the estimator, and there we're specifying that only the second column has to be transformed. We're also making sure that the remainder columns are passed through without any changes. Alright, so now let's continue with our code. We write x equals np.array, open brackets, ct.fit underscore transform x in brackets, comma, dtype equals np.str close brackets, x equals x, open square brackets, colon, comma, 1, colon, close square brackets. So what are we actually doing here? Once we have constructed this column transformer object, we have to fit a transform the dataset to label, encode, and one hot encode the column. To do so, we have our third line of code. It takes the dataset X and transform the values of the attribute geography to numerical using one hot encoder. Moreover, this code takes all values from the transformed X dataset and convert it to an array. This array consists of lists of each row, and all of the values are converted to string using dtype equals np.str augment. In the last line, when we write x equals x, open square brackets, colon, comma, 1, colon, close square brackets, we are ignoring the first index because the same information can be achieved from the index 1 and 2. For instance, values of index 1 and 2 are 0. Then it means the values we lost is 1. Because at a time, geography can have only one location in this way, we have managed to reduce one input neuron without any loss of any information. Now let's print x to see what we get. Let's run this code. So when you run this code, you will get an output like this. The first two columns together are hot encoded for geography. Let's explain the meaning of our output. So, when we see 0, 0, this means France. 0, 1 means Spain. And 1, 0 means Germany. I hope now it's clear how we can convert categorical data, geography in our case, into numerical data, which are combinations of zeros and ones. The next step is splitting the dataset into training and test set. Let's move on and see how we can do this. As we are well aware, to build a machine learning model, we need to construct algorithms that can learn and make predictions on data. The data is usually divided into training and testing data. Training data is a type of data that builds up the machine learning algorithm. The data scientist feeds the algorithm input data which corresponds to an expected outcome. The model evaluates the data repeatedly to learn more about the data's behavior and then adjusts itself to serve its intended purpose. After the model is built, testing data validates that it can make accurate predictions. Test data provides a final real-world check of an unseen data set to confirm that the machine learning algorithm was trained effectively. That's why we have to split the X and Y datasets into a training set and test set. While splitting into training and test set, you have to remember that 80 to 90% of your data should be in the training tests. For implementation, we are going to use the train_test_split method from the sklearn.model_selection library. Let's go to Jupyter Notebook and see how this works. First, we import the library from sklearn.model_selection import train_test_split. Then we write x_train, x_test, y underscore train, comma, y underscore test equals train underscore test underscore split brackets x, comma, y, comma, test underscore size equals 0.2, comma, random underscore state equals 0, close brackets. Here we have four variables: x underscore train, comma, x underscore test, comma, y underscore train, comma, and y underscore test. And we are going to split x into the first two variables and y into the last two variables. We are setting the test size parameter to 0.2, which means 20% of the data are test data and 80% is training data. Moreover, we set random state to 0, which tells our method not to randomly choose rows, so that the corresponding values in all the variables match the same row, and if this code is run again, it should choose the same rows as the first time. So now we have splitted our dataset into x underscore train, x underscore test, y dash train, and y underscore test. Alright, so let's move on with our code. So the next step is feature scaling. Feature scaling is a technique used to standardize the independent features present in the data in a fixed range. As you can see in the dataset, ranges of attributes are not fixed to a specific range. Some have 0 and 1. Some are 0 to 100. Some are 0 to 1 million. Those huge ranges require a lot of time for calculation. So, to overcome this problem, we perform feature scaling. One thing you need to be aware of is that it's better to always perform feature scaling in deep learning, no matter what range your values are in. So let's get started and see how we can do this in Python. So we write from sklearn.preprocessing import standard scaler. SC equals standard scaler. X underscore train equals SC dot fit underscore transform brackets X underscore train close brackets. X underscore test equals SC dot transform brackets X underscore test close brackets. In Python, we use the standard scaler class of the sklearn.preprocessing library. So first we have imported it. Then we have created an object of the imported class. SC equals standard scaler. In the third line of code, we are using the fit transform function as we did previously. This function takes x underscore train as input, then scale each value of x underscore train and returns an array back to the variable x underscore train. And similarly, we are scaling the values of the x underscore test variable. You might have noticed that we use fit underscore transform on the training set, and we only use transform on the test data. We do so because we learn the parameters of scaling on the training data, and at the same time we scale the training data. Now for the test data. We use the scaling parameters learned on the training data to scale the test data. So there is no need for the fit underscore transform for our test data. Slide 60. After performing feature scaling, all values are scaled to a feasible range. Let's confirm this in Jupyter Notebook. Import pandas as PD. Print brackets x underscore train, close brackets. So here we get an array. To get a data frame, we have to write pd.dataframe brackets x underscore train, close brackets. And here you go. As expected, as you can see in this output cell, all values have been scaled to a feasible range. Alright, and now on to the next lecture. Now we are done with the data pre-processing steps. It's time to move to the next part, which is about building the artificial neural network. For this, we use the Keras library. Keras is a powerful, easy to use free open source Python library for developing and evaluating deep learning models. So let's write the following. From tensorflow.keras.models import sequential from keras.models import sequential. From keras.layers import dense classifier equals sequential. We are importing the sequential class from the keras.model library and the dense class from the keras.layers library. The sequential class allows us to build an artificial neural network but as a sequence of layers. As I told you in the theoretical part, artificial neural networks are built with fully connected layers. In order to implement an artificial neural network, we need to initialize our network. We start by creating an object of our sequential class. Classifier equals sequential represents that. By doing so, we have initialized our network as a variable named classifier. Alright, let's now move on to the next step. Now we need to add neurons to our network called classifier. To do so, we call a method named add on the classifier. So let's write classifier.add brackets dense units equals 6, comma, kernel underscore initializer equals uniform, comma, activation equals RELU, comma, input underscore dim equals 11, close all brackets. This is going to add a further component of networks to our model. In our code, this add method takes input from the dense class. Here, dense creates a fully connected two-layer network. This network is composed of 11 input neurons and 6 output neurons. We're going to add more layers like this, so these 6 output neurons will be in the hidden layer of our complete network. The parameters for dense include units. It represents the number of last layer neurons for now. But there is no rule for thumb for taking 6 neurons. You can use any other number and check. The next parameter is kernel underscore initializer. The neural network needs to start with some weights and then iteratively update them to better values. The term kernel underscore initializer is a fancy term for which a statistical distribution or a function is used to initialize the weights. In case of a statistical distribution, the library will generate numbers from the statistical distribution and use them as starting weights. In our code, the value for this parameter is uniform. This means that all weights will be uniformly distributed in our network at first. Alright, the next parameter is activation, which refers to the activation function. We have used the rectifier activation function, RELU. And now onto the last parameter. It is input underscore dim, which means dimension of input neurons. In our case, it is 11. Why is it 11? Because we have 11 independent variables, including 2 columns of geography. That's why input dim equals 11. Okay, so now we have built our first input layer and one hidden layer. In the next step, we'll build the next hidden layer. Alright, so to add the second hidden layer, let's write classifier.add brackets dense units equals 6, comma, kernel underscore initializer equals uniform, comma, activation equals RELU, close brackets. This is the same code as the previous one, except that here we do not need the input dim parameter because it automatically connects to the previous layer of our network. So 6 neurons from the previous layer will be input to this layer. The rest of the code is same. This new layer consists of 6 neurons again. Weights are initialized uniformly, and we are using the rectifier activation function again. Now we have added one input layer and 2 hidden layers. It's time to add our output layer. Let's see how we can do this. In the output layer, we need 1 neuron. Why do we just need 1 neuron? Because, as you can see in the dataset, we have dependent variable in binary form. This means we have to predict in a 0 or 1 form. The customer will leave if it is 1 and stay if it is 0. That's why only 1 neuron is enough in the output layer. Okay, so to add the output layer, let's write classifier.add open brackets dense units equals 1, comma, kernel underscore initializer equals uniform, comma, activation equals sigmoid, close brackets. This line of code is similar to the previous one, but here the units parameter of a dense is 1 because we know that 1 neuron is enough to predict the output. It's either 0 or 1. Moreover, the activation function used here is the sigmoid activation function. Why? Because the sigmoid activation function provides the probability of a customer staying in the bank or leaving the bank. Alright, now on to the next lecture. Okay, so now we are finally done with the creation of a structure for our first artificial neural network. In the next step, we need to compile this network, and we also need to fit our data to this structure and tune this network according to our data. We do this by providing the training data to the network. So let's begin the compilation process of our artificial neural network. We write the following: classifier.compile open brackets optimizer equals Adam, comma, loss equals binary underscore cross entropy, comma, metrics equals square brackets open accuracy square brackets close all brackets close. Compile is a method of the TensorFlow library, which compiles the artificial neural network together. The first parameter is the optimizer. Its value in our code is Adam. This performs the stochastic gradient descent optimizer technique. Next is the loss parameter, which represents the loss function. It is an optimization function which is used in case of training a classification model, which classifies the data by predicting the probability of whether the data belongs to one class or the other. One thing you need to be aware of when you are doing a binary prediction similar to this one, always use the loss function as binary underscore cross entropy. The binary cross entropy function computes the cross entropy loss between true labels and predicted labels. Alright, so the third parameter is about the evaluation of our network. To evaluate our artificial neural network model, I'm going to use the accuracy metrics. Accuracy metric calculates how often predictions equal labels. This metric creates two local variables, total and count, that are used to compute the frequency with which y underscore pred matches y underscore true. With this, we have compiled our artificial neural network model, and now on to the next lecture. Our next objective is to fit our data set to our model. To do this, we use the fit method that takes 4 arguments. Let's do it in Python. So we write classifier.fit brackets x underscore train, comma, y underscore train, comma, batch underscore size equals 10, comma, epochs equals 100, close brackets. First, we have the values for the input neurons. In this case, it is x underscore train. The second argument is the values for output layer neurons. The third argument is the batch size. Instead of comparing our predictions with real results one by one, it's better to perform this task in a batch. So we assigned value 10 to batch size. So at a time it takes 10 rows. And the last argument is epochs. An epoch is defined as the number of times an algorithm visits the dataset. In other words, epoch is one backward and one forward pass of all the training examples. The neural network has to train on a certain number of epochs to improve the accuracy over time. So I decided that the epochs equal 100. And when you run this code, you can see the accuracy in each epoch. In the first few epochs, the accuracy scores are the following, which is around 80%, but after running all 100 epochs, the accuracy increases and we get the final accuracy, 85.44%. And this is quite good. Now we are done with the training part. The last but not least part is predicting the test set results. Let's see how we can do this. Once our model is trained, we want to see how our model is predicting using x underscore test data. So let's write the following lines of code regarding prediction. Y underscore pred equals classifier dot predict open brackets x underscore test close brackets y underscore pred equals brackets y underscore pred greater than 0.5 close brackets. What we're doing here is the following. We are defining that if y underscore pred is in between 0 and 0.5, then this new y underscore pred will become 0, false. And if y underscore pred is larger than 0.5, then the new y underscore pred will become 1, true. Let's see what inside y underscore pred. So we write print, open brackets, y underscore pred, close brackets. You can see the predicted values for x underscore test data on the screen. But can you know how many values are predicted right? And how many values are predicted wrong by looking at your screen? Well, for a small dataset, you can. But when we have a large dataset, it's quite hard to count one by one. That's why you use a confusion matrix to clear out confusion. So we need to write the following code. skilllearn.metrics import confusion underscore matrix, comma, accuracy underscore score. CM equals confusion underscore matrix, open brackets, y underscore test, comma, y underscore pred, close all brackets. Print CM. Accuracy underscore score, brackets, y underscore test, comma, y underscore pred, close brackets. Let's run this code. A confusion matrix is also known as an error matrix. It is a summary of prediction results on a classification problem. The matrix you see on your screen is a confusion matrix, which tells us that 1499 true values are correctly predicted true. 96 false values are incorrectly predicted true. 189 true values are incorrectly predicted false. 216 false values correctly predicted false. So, the confusion matrix gives more information than just accuracy on how much values are correctly predicted. And we got 85.75% accuracy. That's not bad. Now I would recommend you experimenting with some values and let me know how much accuracy are you getting. Alright, so that was it for the construction of the artificial neural networks. Congratulations! You have now successfully built your first artificial neural network. Now it's time to wrap up with a small quiz. Quiz time. The number of nodes in the input layer is 10 and the hidden layer is 5. The maximum number of connections from the input layer to the hidden layer are... I hope you're now ready with an answer. So the answer is option A, i.e. 50. Since the multilayer perceptron, or MLP, is a fully connected directed graph, the number of connections is a multiple of the number of nodes in the input layer and the hidden layer. In the past few decades, deep learning has proved to be a very powerful tool because of its ability to handle large amounts of data. The introduction of hidden layers has surpassed traditional techniques, especially in the pattern recognition. One of the most popular deep learning neural networks is the convolutional neural network, or CNN. CNNs have become a very important part of many computer vision applications. In this course, we'll explore this very important neural network called convolutional neural network. So, let's get started and see how it works. Slide 74. CNNs were first developed and used around the 1980s. The most a CNN could do at that time was to recognize handwritten digits. It was mostly used in the postal sectors to read zip codes, PIN codes, and so on. The important thing to remember about any deep learning model is that it requires a large amount of data to train and also requires a lot of computing resources. This was a major drawback for CNNs at the period, and hence CNNs were only limited to the postal sectors, and it failed to enter the world of machine learning. In 2012, Alex Krzyzewski realized that it was time to bring back this branch of deep learning that uses multi-layered neural networks. The availability of large sets of data and abundance of computing resources enabled researchers to revive CNNs. In deep learning, a convolutional neural network, known as CNN or ConvNet, is a class of deep neural networks most commonly applied to analyze images. Now, when we think of a neural network, we think about matrix multiplications, but that is not the case with ConvNet. It uses a special technique called convolution. What is convolution? It is simply a mathematical operation on two functions. When two functions, f and g, are combined mathematically, the result is a third function that expresses how the shape of one is modified by the shape of the other. So, in mathematics, and specifically functional analysis, convolution is a mathematical operation on two functions, f and g, that result in a third function that expresses how the shape of one is modified by the shape of the other. The word convolution refers to both of the outcome function and the technique of calculating it, and it is used interchangeably. After one function is reversed and shifted, the convolution is defined as the integral of the product of the two functions after they've been combined together. The integral is calculated for all possible values of shift, resulting in the convolution function being produced. Slide 75. In a convolution neural network, our input image can be either grayscale or colorful. Every image is made up of pixels that range from 0 to 255. We need to normalize them, which means that we need to convert the range between 0 and 1 before passing it to the model. Let's now explore the components of the convolutional neural networks in detail. Slide 77. The CNN model works in two steps: feature extraction and classification. Slide 78. Feature extraction is a phase where various filters and layers are applied to the image to extract the information and the features out of it. And once it's done, it is passed on to the next phase, which is classification. During classification, the information and the features are classified based on the target variable of the problem. A typical CNN model looks like this: input layer, convolution layer plus, activation function, pooling layer, fully connected layer. Here is an example of an input image of size 4x4 that has 3 channels, i.e. RGB and pixel values. Slide 80. The convolution layer is the layer where the filter is applied to our input image to extract or detect its features. A filter is applied to the image multiple times and creates a feature map which helps in classifying the input image. Let's understand this with the help of an example. For simplicity, we'll take a 2D input image with normalized pixels. In the figure, we have an input image of 6x6, 6x6, and applied filters of 3x3 on it to detect some features. In this example, we have applied only one filter, but in practice, many such filters are applied to extract information from the image. Slide 81. The result of applying the filter to the image is that we get a feature map of 4x4, which has some information about the input image. Many such feature maps are generated in practical applications. Let's get into some math behind getting the feature map in the following image. So, as presented in the figure, In the first step, the filter is applied to the green highlighted part of the image, and the pixel values of the image are multiplied with the values of the filter, as shown in the figure using lines, and then summed up to get the final value. Slide 82. In the next step, the filter is shifted by one column as shown in the image. This jump to the next column or row is known as stride, and in this example we are taking a stride of 1, which means we are shifting by one column. Slide 83. Similarly, the filter passes over the entire image and we get our final feature map. Once we get the feature map, an activation function is applied to it to introduce non-linearity. I hope you remember that an activation function in a neural network defines how the weighted sum of the input is transformed into an output from a node or nodes in a layer of the network. A point to note here is that the feature map we get is smaller than the size of our image, because when the center of our filter sits on a value to change, other values of the filter must also sit on some values. In our case, the center of the filter cannot sit on the outermost values of our image, so we have lost a layer from each side. If our filter is 5 by 5, then we will lose 2 outermost layers from all sides. So as we increase the value of stride, the size of the feature's map decreases. The pooling layer is applied after the convolutional layer. It is used to reduce the dimensions of the feature maps. Thus, it reduces the number of parameters to learn. It preserves the important information or features of the input image. Pooling is a method used to convert an input image to a lower resolution version, which still contains the large or important elements of the input image. The most common types of pooling are max pooling and average pooling. Max pooling extracts the maximum value of the area it convolves, and average pooling computes the average of the value of the area it convolves. The average pooling method smooths out the image, and hence the sharp features may not be identified when this pooling method is used. Max pooling selects the brighter pixels from the image. It is useful when the background of the image is dark and we are interested in only the lighter pixels of the image. The image on our screen shows how max pooling works. Using the feature map which we got from the previous example, we apply max pooling. Here we are doing max pooling of size 2 by 2 with a stride of 2. The maximal value for each highlighted area is taken and a new version of the input image is obtained which is of size 2 by 2. So, after applying pooling, the dimension of the feature map has been reduced. Alright, so till now we have performed the feature extraction steps. Convolution plus pooling combinedly extract different features from an image. For example, the edges of a shape in an image can be detected. If the image is an image of a face, then the eyes, nose and mouth can be detected. After the convolution plus pooling layers, we add a couple of fully connected layers to wrap up the CNN architecture. This is the same fully connected ANN architecture we talked about in the previous part of artificial neural networks. Remember that the output of both convolution and pooling layers are two-dimensional, but a fully connected layer expects 1D vector of numbers. So, we flatten the output of the final pooling layer to a vector, and that becomes the input to the fully connected layer. Flattening is simply arranging the 2D numbers into a 1D vector. Nothing fancy happens here. These fully connected layers connect the information extracted from the previous steps, i.e., convolution layer and pooling layers to the output layer, and eventually classifies the input image into the desired label. The complete process of convolutional neural network model can be seen in the image. Alright, and now on to the next lecture. Alright, so now we understood the theory that powers convolutional neural networks, let's dive into the implementation part of CNN. Let's see how we can implement all of this in Python. Slide 87. We are going to use the MNIST handwritten digit data, which contains the image of handwritten digits. Slide 88. We know a few things about the dataset. The images are all pre-aligned. Each image only contains hand-drawn digit. And we also know that the images all have the same square size of 28 by 28 pixels, and that the image are grayscale. Hopefully, now you have a good understanding of convolutional neural networks. It is time to implement it in Python. First of all, we'll start by importing all the required libraries for the CNN model. So let's go to the Jupyter Notebook and do this. We write from tensorflow.keras.datasets import MNIST from tensorflow .keras.models import sequential from tensorflow .keras.layers import conv2d from tensorflow .keras.layers import maxpool2d from tensorflow.keras.layers import flatten from tensorflow.keras.layers import dropout from tensorflow.keras.layers import dense. In the first line, we are importing the MNIST dataset of images. The model type that we will be using is sequential. We are importing this model from Keras models. Sequential is the easiest way to build a model in Keras. It allows you to build a model layer by layer. We are dealing with two-dimensional images, so we import conv2d. It's basically a two-dimensional convolution to help us in the convolution layers. Similarly, we are importing other required libraries that we need for the construction of a convolutional neural network in Python. The usage of these libraries will be explained in the upcoming lectures. The MNIST dataset is conventionally provided to us as part of the Keras library, so we can easily load the dataset. Let's see how we can do this. So we write, here we are loading the data. Brackets x underscore train, comma, y underscore train, comma, brackets x underscore test, comma, y underscore test equals mnist dot load underscore data brackets. Here we are reshaping the data. X underscore train equals X underscore train dot reshape brackets X underscore train dot shape open square brackets 0 close square brackets comma X underscore train shape open square brackets 1 close square brackets comma X underscore train dot shape square brackets open 2 close square brackets comma 1 X underscore test equals X underscore test dot reshape brackets X underscore test dot shape square brackets open 0 close square brackets comma X underscore test dot shape open square brackets 1 close square brackets comma X underscore test dot shape open square brackets 2 close square brackets comma 1. Here we are checking the shape after reshaping. Print brackets X underscore train dot shape. Print brackets X underscore test dot shape. And here we are normalizing the pixel values. X underscore train equals X underscore train divided by 255. X underscore test equals X underscore test divided by 255. Let's run this cell. And here we go. We have an output. Out of the 70,000 images provided in the data set, 60,000 are given for training and 10,000 are given for testing. When we load the data set, X underscore train and X underscore test will contain the images, and Y underscore train and Y underscore test will contain the digits that those images represent. Our next objective is to reshape the size of the images. We know all images are grayscale and have the same size of 28 by 28 pixels. But in most real-life problems, we do not get the same property from the images. So it is better to resize all images to a specific size and color. We do so by using the reshape method, which takes 4 arguments. The first argument is for the number of images. The second is the number of pixels in a column of image. The third is the number of pixels in a row. And the fourth is argument represents the color. For X underscore train, in our case, the first argument is gonna be 60,000. Because we know it already, the second and third are gonna be 28 because the size of all images is 28 by 28. And in the last argument, 1 indicates grayscale. The same goes for X underscore test. The only difference is that the first argument would be 1,000. In order to check the shape, we wrote print brackets X underscore train dot shape. Print brackets X underscore test dot shape. And we got our output. We know that the pixel values for each image in the dataset are unsigned integers in the range between black and white, or 0 to 255. We do not know the best way to scale the pixel values for modeling, but we know that some scaling will be required. A good starting point is normalize the pixel values of grayscale images Example, rescale them to the range 0 to 1. This involves first converting the data type from unsigned integers to floats, then dividing the pixels values by the maximum value, 255. Let's see how we can do this in Python. Our data is ready, and now is the time to define a baseline, convolutional neural network model for the problem. We do so by this first line of code. Model equals sequential. The model has two main aspects: the feature extraction, which consists of convolutional and pooling layers, and the classifier fully connected layers that will make a prediction. Next, we are adding a convolutional layer. We write model.add brackets conv2d brackets 32 comma brackets 3 comma 3 comma activation equals RELU comma input underscore shape equals brackets 28 comma 28 comma 1 close brackets. Here we are specifying 32 filters with size of 3 by 3. We are using the rectified linear unit activation function in our layer. Moreover, the input image has a size of 28 by 28, and they are grayscale. Next, we need to apply the max pooling layer. Let's do this. So we write model.add brackets maxpool 2d brackets 2 comma 2 close brackets. The size of max pooling is 2 by 2, which means it will take the maximum value from the 2 by 2 matrix of pixels. Let's carry on with our code. So we write adding fully connected layers as a side note. Model.add brackets flatten close brackets model.add brackets dense brackets 100 comma activation equals RELU close brackets. In between the conv2d layers and the dense layer, there is a flattened layer. Flatten serves as a connection between the convolution and dense layers. Dense is the layer type we will use for our output layer. Dense is a standard layer type that is used in many cases for neural networks. The flatten method arranges the pixel values from 2D images to 1D array. We are adding a dense layer of 100 neurons in our output layer using the rectified linear unit activation function. Alright, so let's carry on with our code. We write adding output layer as a side note. Model.add brackets dense brackets 10 comma activation equals of t max close brackets. So here we are adding another dense layer of 10 neurons in our output layer. Because we know that there are only 10 digits 0 to 9, the activation is soft max. Soft max makes the output sum up to 1, so the output can be interpreted as probabilities. The model will then make its prediction based on the option that has the highest probability. Alright, so once our network is ready, we need to compile it in the same way as we did in our previous activity. The only difference we have here is that we are using sparse categorical cross entropy loss function instead of binary cross entropy loss function, because this is a categorical problem, while the previous coding exercise was a binary classification problem. So let's carry on with the code. We write compiling the model as a side note. model.compile brackets loss equals sparse underscore categorical underscore cross entropy comma optimizer equals Adam comma metrics equals square brackets accuracy close square brackets close all brackets. The last step of finalizing our CNN is fitting our dataset to our model. So let's write fitting the model as a note. Model dot fit brackets x underscore train comma y underscore train comma epochs equals 10 close brackets. So to fit our dataset to our model, we are using the fit method. Moreover, we are specifying epochs as a 10, which means that our model will go through our dataset 10 times. Let's run this code and see what we get. We'll wait till our model is trained and all the epochs are completed. And ta-da! Our CNN is now trained. It is now the time to evaluate our model. So we write evaluating the model as a note. Then model.evaluate brackets x underscore test comma y underscore test close brackets. Amazingly, the accuracy of our model is 98.64%. Congratulations! You have now built your first CNN model.